Recording. Okay, and now let's take a look at the lesson for today. Um, Today we're going to look at uh, electrolysis. Electrolysis is an electrochemical reaction that isn't spontaneous uh, by itself and has to be driven by the input of some kind of electrical energy from outside. You're going to effectively attach a battery to it and make the reaction go the direction you want it to go, even though that direction isn't spontaneous. Um, Now, inside metals, metals are excellent conductors of electricity. And we talked about that in Gen Chem 1, about how the valence electrons in a metal essentially can migrate throughout the entire sample of metal. And you can put one electron into the metal somewhere, and that cloud of electrons dumps one out the other side. And so they have excellent conductivity for electrons um, inside the metal itself. Or you can have some conductors that have missing spots for electrons. Those electron holes can also be conductors. In solution, though, current is carried by the migrations of ions under the electric field of the electrodes. The positive ions, cations, in the solution will be attracted to the negative electrode, and likewise the negative electrons attracted to the positive electrode. And when those particles get over to the electrodes, an electrode reaction can take place there that causes the current to be transferred from the negative electrode to the positive one through the solution. You cannot have electrons in solution. They have to be carried by charges of ions. Now, we're going to count electrons the way we counted matter. We counted atoms by looking at Avogadro's number, and that was a mole. And a mole of electrons is 96,500 coulombs. Now, you do have to kind of get these units together. A coulomb is amps times seconds. So if you pass a current for 1 amp at 1 second, that would give you 1 coulomb of charge. And 1 mole of those would be 96,500 coulombs, or 96,500 amp seconds is a mole of electrons. And this 96,500 coulombs is called the Faraday constant. The number of moles of electrons passed during an electrolysis can be used to calculate the amount of each species involved in the reaction. You're going to do stoichiometry just like we did. We're just going to look now at the electrons transferred. And we can use our method of doing stoichiometry just like we always have and calculate the amount of current, the number of moles of electrons it would have to pass in order to undergo 1 mole of oxidation or reduction. Now, we do have a lot of industrial applications of electrolysis. The most notable one, really, I think, is aluminum. Aluminum is the most abundant element on Earth, yet for most of our history, it was extremely expensive because you couldn't get it from its ore. The oxide of aluminum is extremely stable, and you can't just throw a little bit of charcoal in it and stew it up and reduce the aluminum out of that oxide like we do iron from iron ore. But with the advent of cheap electricity, we were able to electrolyze aluminum directly, and we can then take aluminum oxide and dissolve it in chloride like hydrochloric acid or something like that, and then carry out the electrolysis and reduce the aluminum to ion to aluminum metal. And it's the industrial way that we make aluminum. Sort of an interesting story I learned was that one of the kings of France, I don't remember which one, but he was very opulent, and he had all this gold, these gold utensils in the palace. So he commanded that they all be eliminated and get aluminum instead, because aluminum was more expensive than gold. Well, not such good practice in the long run. So we do electroplate and refining by reduction using aluminum, using electrolysis. Aluminum, magnesium, sodium, almost all of the very reactive metals also are made by electrolysis of molten salts. We produce hydrogen, chlorine, and sodium hydroxide from salt water that way. And actually, we're not interested so much in the hydrogen. I've already told you, we can get hydrogen cheaper from petroleum refining than we can get it by electrolysis. But chlorine and sodium hydroxide are very important to us. And if you just take saturated salt water, you can electrolyze that and you can produce chlorine and sodium hydroxide from that. Now, I'm going to just mention this because it's mentioned in your book. Corrosion is a redox reaction, and you can prevent this, but it's not real easy, and you have to sacrifice a more reactive metal in order to prevent corrosion. So generally, when you get a rusty spot on your car and it pops the paint off, that's because under that rusty spot, there's really a crystallite of a different metal other than iron. And those dissimilar metals form an electrochemical cell that causes the iron to convert to the oxide, and you produce more and more rust with the air that's present. So a good coat of paint will help that, but corrosion tends to be very, very prevalent, and it's we can stop the corrosion by coating with metals like tin or zinc. We still call the cans that canned food is in a tin can, although it certainly never was tin. Tin's extremely soft. So what they did was they took the iron can and dipped it into tin and put a thin layer of tin on it that would protect it from corrosion. Similarly, we make buckets out of iron, but we dip them or electrolyze zinc onto them to create galvanized metal containers. And in each case, the coating is able to protect from corrosion. And you can protect metals by cathodic protection. That is, you add a more reactive metal, just solder in a wire and attach it to a more reactive metal. And then when corrosion occurs, it'll occur at the more reactive metal instead of at the iron. And magnesium is often used for that. It's kind of funny, I don't know what it matters, but most coffins have a great big bar of magnesium on the bottom. And that's attached to the coffin so that when it's buried in the moist soil and good environment for corrosion, the coffin will last longer, but it won't last forever. And what's inside it won't last forever, but the soul that was in it does. Okay, let's look at some problems. Write the oxidation, anode, and reduction cathode cell for each of the electrolysis that occurs during the electrolysis of molten sodium bromide. Now, if you melt sodium bromide, you're going to have sodium ions and bromide ions in the melt. So what would happen then is the sodium ions would be reduced And now remember this, reduction always occurs at the cathode of the cell. So if you want to know which cell is the cathode and which one is the anode, look and see that you have reduction. Reduction occurs at the cathode, oxidation occurs at the anode. So the oxidation reaction is to take two Br minus ions and convert to liquid bromine and 2 electrons. So it is the loss of electrons, as we said, but that oxidation occurs at the anode of the cell. Right, the oxidation, anode and cathode reaction that occur during the electrolysis of sodium bromide. Okay, the reduction is the sodium ion, and its voltage is minus 2.71 volts. Now notice it's a standard voltage. Always when we're measuring voltages, we have to have two electrodes. One electrode will be positive, the other one will be negative, and we'll measure the voltage between those two electrons. It's really called a potential difference, and that's what it is. It's always a difference. But what we've done to create a standard cell in electrolysis is we have the hydrogen reduction, and we establish that to be 0 voltage. So if I have an electrode, the standard electrode with hydrogen and hydrogen ion on that electrode, and sodium ion on the other electrode, and then I measure the voltage between those two, I'm going to measure negative 2.71 volts. So the negative means the spontaneous direction is actually the other direction relative to hydrogen. The sodium would go to sodium ion and release an electron. So just like in every case in Hess's law, if we turn a reaction around, we change the sign of its functions, including the voltage. Voltage then for the sodium reduction is negative 2.71 volts. If I look at water reduction, water reduces also to hydroxide ion and hydrogen, and its voltage is negative 0.83 volts. Now let's look at oxidations that could be taking place now in an aqueous solution. Distinguish us now from the molten chlorides that we had above. Above we didn't have to worry about water. But in aqueous solution, water is going to provide both a reduction reaction and an oxidation reaction. In the case of the bromide ion, we are going to oxidize bromide to bromine liquid and 2 electrons. That voltage occurs at minus 1.06 volts. And the water oxidation occurs at minus 1.23 volts. Now, we're going to have to pick one of the reductions and one of the oxidations. The reduction that occurs in real life is always going to be the one with the most positive potential. So comparing sodium and water as reductions, water is reduced at minus 0.83 volts, but you'd have to go all the way to minus 2.71 volts in order to reduce sodium ion. So the reduction that's going to take place in aqueous solution for the cathode reaction is going to be the water reduction. Now, if I compare the bromine and the water oxidations, the oxidation that's most positive is the 1.06 volts for oxidizing bromide ion compared to minus 1.23. So the two reactions that are going to take place in this cell is at the reduction cell, at the cathode, we're going to cause reduction of water. You're going to have hydrogen gas bubbling off at that electrode, and you're going to have hydroxide ion occurring in the solution around that electrode. At the cathode, at the anode cell, we're going to have the bromide oxidation take place. So the best overall reaction is this one. And that's the reaction that will actually take place. remember, we have to add these two together and cancel out their electrons. So the two waters and the two bromide ions are the reactants. The hydrogen hydroxide and bromine liquid are the products. And the voltage that would be needed to make that happen is minus 1.83 volts, 89 volts. You have to add the two voltages together algebraically. And in this case, that means that you wouldn't, say if I had a flashlight battery of 1.5 volts, I can't carry out that reaction in water. That reaction shouldn't take place. But if I had a voltage that put two batteries together, yes, then I could. Now let's look at some interesting comparisons, I think, to give you an illustration of how much energy is involved in carrying out an electrochemical reaction. 100-watt light bulb draws approximately 0.909 amps of current. How long would it take this current to deposit 1 ton of aluminum from Al2O3? The Hall-Herlo process is the name of the reaction that we use to do that. Okay, we have 9.08 kilograms. We got to convert from kilograms to grams. That's the only way I know to do it. And then I want to go from moles of aluminum to grams of aluminum. So the amount of aluminum is given up till now. It takes 3 moles of electrons to deposit 1 mole of aluminum. And now it takes 96,500 amp seconds to be 1 mole of electrons. Cancel out the units. And we get 9.736 times 10 to the 9th amp seconds. The current carried by the light bulb is 0.909 amps, so we can calculate the seconds. So let's convert that into, that's a big, big number. So let's convert that into days and in years. It would take 340 years for a 100-watt light bulb to draw as much current as we use in making just 1 ton of aluminum. And the aluminum plant up in Kentucky, not far from here, does probably several tons a day. So you can imagine whenever that plant goes online, it probably dims all of the light bulbs in the whole county. Okay, here's a checkpoint for you on this. A spoon is being coated with gold from a solution of potassium hexacyano-RO3. Okay. What mass of gold? Oopsie daisy. I need to go back where I was. Okay. I think I'm going to have to drop that. Okay. Don't quite know what happened there, but okay. All right. Trying to get back to where we were when we lost that. Okay. Actually, what happened is we finished that segment, so we need to open up the next segment. And okay. All right, now let's go back to screen share and we should be okay. All right. Now, a voltaic cell or a galvanic cell is a spontaneous reaction. Now, it's one that will happen all by itself. In the non-spontaneous electrolysis reactions, we didn't have to worry about keeping the reactants and products apart from each other or keeping the two reactants away from each other. Because the reaction was not spontaneous, it was going to be driven from a voltage from the outside in our laboratory. So if we've got a galvanic cell, a cell that is spontaneous, we can't put the reactants and products together. If you do, the reaction will take place all by itself. There won't be any voltage generated. There won't be any work done. No electrical work at all will be done in that kind of process. But the galvanic spontaneous cells are, again, the ones we would like to do. It's far more interesting to create something that would give us a really good battery, a spontaneous cell, and than it is to imagine just any old electrolytic cell. We can perhaps do that if we can find enough voltage to do it and wait long enough. So you have to keep those two separated from each other. We do that with what's called a salt bridge to provide a pathway through the cell for the ions to migrate. So if I've got a cathode in one cell and an anode in the other cell, I have to put them in separate containers, and then I can put a salt bridge across them to connect the two cells. And the salt bridge will contain generally potassium chloride. It's what we use most of the time. In a lab experiment we used to do for your lab, we would do that by using a paper towel dripped in salt water. But it does allow the positive and the negative ions within the salt bridge to go into any one of the two compartments. So for example, if one compartment is reducing metal ions to metal, then what's going to happen is the metal ion cation is going to be disappearing out of that solution. Well, in order to maintain neutrality, some potassium ions can come out of the salt bridge and go into that solution to replace the metal cation that disappeared. And then likewise, the chloride would drop out into the other cell. So you would wind up then keeping things happening. Again, remember, oxidation still occurs at the anode. And you add the anode and cathode reactions to produce the cell reaction that you have, just like we did before. Now, the voltage of a cell represents potential difference, the potential energy difference between an electron on one of those electrodes moving to the other electrode. It's the potential energy difference between those two. And that gives the driving force for the oxidation half reaction and for the reduction half reaction. Now, we have to always have a zero that we call a ground. And it's an arbitrary thing, just like you remember when we talked about standard states for elements, we said we could make up any reference state we wanted to, but we chose the one that had the elements in their natural native state at 25 degrees and 1 atmosphere pressure of that substance, gaseous substance, made up the standard state for that substance. And we just called it zero. We're going to do the same thing for electrode reactions, either cathode or anode reactions. And we have to choose one that we're going to arbitrarily call a zero. And that is the ground voltage. Now, is that voltage zero? Absolutely not. Let me tell you another story. My mom was almost electrocuted because we got little baby chickens, and we get them before the end of winter or in early spring, and we kept them in the little chicken coop outside, and we had to keep a light bulb in there to keep them warm. So my mom went out one day, and it's early in the spring, and it's really nice weather. She went out barefoot, and she went and saw the light bulb was out. So she just started unscrewing the light bulb. Well, she unscrewed it, but she wasn't careful. She had her hand down on the bottom of the light bulb, and she unscrewed that, and she was touching then the metal electrode that was the ground electrode. Well, she was actually taking 110 volts then, and it would have killed her had she not uh, put her foot back up on the little wood doorway that led into the chicken coop. And when she put her weight on it to pull herself loose from that wire, the minute she got her feet up off the earth ground, then the voltage stopped and the light bulb flew out of her hand, and she was not killed. If she couldn't have done that, it would have killed her. So the voltage of that quote ground electrode isn't really zero. We've just called it zero, and that's what they've done when they wired the electrical wiring. So one of the electrodes is a common electrode, and it's usually attached to earth ground. And that way, if you touch the wide wire plug on your plug, if you touch that from one circuit to another, you're probably going to be okay. If you touch the smaller one, either one of them, you'll probably be okay. But if you touch the wide one and the narrow one, you will not be okay. You will get a very high voltage. And if you touch either one of them standing on the ground without your shoes on, you'll understand that neither one of them is ground. So it's an arbitrary decision, and we choose the hydrogen half cell. In either oxidation or zero, it's assigned to zero voltage. So if I take hydrogen ion and reduce it to hydrogen gas, that voltage is zero. Or if I take hydrogen gas and oxidize it to hydrogen ion, that voltage is zero. We keep that as our reference voltage. The voltage then of the other electrodes are assigned the value we measure when we measure the voltage of that electrode against the hydrogen electrode. And that gives us the voltage for the other cell. Now, the voltage of the cell becomes more positive if the concentration of or pressure of the reactants is increased. Remember Le Chatelier's principle? We want the voltage to the right to be positive. So if we increase the pressure of gaseous reactants, then Le Chatelier's principle says that'll go to the right. And if that goes to the right, that increases the voltage. And likewise, you can increase the voltage if you decrease the concentration of the products. Remember, every reaction is really an equilibrium. So if you take away things in the product, then Le Chatelier said it would shift to the right again, and that gives us the positive direction. The standard voltage of the cell is the voltage generated as reduction when combined with the hydrogen electrode. Now, all the concentrations have to be at 1 moles per liter concentration, and all gases have to be at 1 atmosphere to give us the standard voltage. Changing concentrations, changing gas pressure, changes the voltages. Now, when you put two reactions together, you see, when I said we want this other electrode that we added to be in reduction, that means electrons are going to go into the circuit on that side to cause reduction to take place. And if you wanted electrons to go into that, you would attach, say, a negative electrode to it to push electrons in that direction. But whenever you put two things together a reaction will occur. And the reaction that does occur is the spontaneous one. And nature do what nature do. You can write the reaction from reactants to products on your scrap paper, but that's not any assurance that nature's going to follow your lead. Nature's going to do what nature do, okay? So the spontaneous reaction will occur, whether it's the one you wrote from left to right on your scratch paper or the opposite. One of those two will occur. It's the one that generates the positive voltage. If you reverse the direction of a reaction, you reverse the sign of the voltage. A spontaneous reaction generates a positive voltage. If the non-spontaneous electrode is in one direction, the spontaneous voltage is in the opposite direction. So that's the one that's going to occur. Now, we're going to add two voltages together to get the voltage of an overall cell. We're going to add the oxidation voltage and the reduction voltage together. The voltage corresponds to standard concentration in the mixture. Now, you remember what we talked all the time about, what the standard mixture means. If you've got gases and reactants and products, each one of them is at 1 atmosphere pressure. If you've got ionic components dissolved in solution, each one of them is at 1 molar concentration, whether or not it's a reactant or a product. Remember the standard set of concentrations, and when we talk about voltages, it'll be voltages with little superscripts over them, would be the standard voltage. And that's going to be the reaction that's going to take place is the one that generates the positive voltage. Okay, here's some problems. This one I thought was kind of interesting because I essentially changed one of the electrodes in the common lead storage battery to aluminum. And if I'm looking at this reaction, it's pretty obvious that the aluminum on the left is at 0 oxidation number. The aluminum on the right is at +3. So that's got to be the oxidation or anode reaction taking place. It's going to generate electrons on the metal aluminum. So the aluminum metal is going to be the negative electrode. It's going to be the electron where oxidation takes place, and oxidation makes that the anode. If you look at the other substances, lead and the lead-4 oxide on the left is in +4. Lead-2 sulfate is a form of lead on the other side. And on the other side then, the oxidation number of lead is 2. It goes from 4 to 2. That's reduction. Here's what the cell would look like. You've got an aluminum cell in the presence of aluminum ion. You've got a lead sulfate cell with lead dioxide coating its surface. So the lead sulfate is actually on a real car battery. The lead sulfate is also attached to a lead electrode that comes out the top of the battery. So, but the lead sulfate reaction here is going to be the positive electrode, because we saw when aluminum comes out into the solution to make the +3 ion, its 3 electrons stay on that electrode. So this electrode, the aluminum electrode, is negative. Okay, so now let's define the standard cell for that electrode and the direction the reaction will proceed from the standard mixture once it's assembled. So the standard cell consists of a cathode made of lead sulfate covered with solid lead dioxide in the solution that contains 1 molar hydrogen ion and 1 molar sulfate ion. So the lead dioxide to lead sulfate electrode, the lead sulfate is the one that's on the outside, it's the one that's formed in that reaction. A reduction has occurred there. This is a balanced electrochemical cell for that. The cell voltage is 1.68 volts. You can look that up in the table. An anode made of aluminum is in a solution of 1 molar aluminum ion. The reaction as it's occurring is at 2 aluminum solid atoms go to 2 aluminum plus 3 aqueous ions and 6 electrons. Again, you can look up that voltage. It's at plus 1.66. Now, we've got the same number of electrons gained and lost in these two. We can add the two together to get the overall cell voltage. It's 3.34 volts. Just adding these two numbers together, since they both have the same sign, we'll add them and keep the sign. It's positive. So this reaction is spontaneous, and it'll generate 3 1/3 volts per cell. Now this is with these standard concentrations. You've got to remember, what would happen to the cell voltage if barium plus 2 is added to the cathode compartment, hydrogen is added to the anode compartment, OH is added to the anode compartment, and water is added to each compartment. Okay, cathode. This is the cathode reaction we had. And now, if you look at this reaction, we're talking about adding barium ion to this. And I'm looking at all of this and I'm saying, well, barium's not going to react with this, but it could bump into sulfate. Barium sulfate is insoluble. So if I put barium ion into this electrode, I'll precipitate some barium sulfate out of that electrode, which means this reactant is going to be decreased. If I decrease that concentration, it would decrease its voltage. So the standard cell would decrease that cell voltage over what we had up above. Now, if I add hydrogen ion to that compartment, I'll increase the concentration of hydrogen ion, which Lissatelier says should shift to the right. Since the voltage is positive, going to the right, then that will cause the voltage to increase. So adding more hydrogen ion would make that reaction more spontaneous. Adding water will decrease the concentration of the things it can do. Look here, I'm going to decrease the concentration of sulfate, I'm going to decrease the concentration of hydrogen ion, and I'm going to do nothing to the rest of the things, because you can't change the concentration of water in water by adding water. It's still water, okay? So it decreases the concentration of reactants. Lissatelier says that shifts to the left. That would cause a decrease in the voltage that occurs. Okay. Okay. Now, here's another problem. It's very similar to that. I've given you I've given you reduction reactions for all the things that are involved in this. The nickel 2 oxide is a coating here on the nickel metal, and it can undergo this reduction, and from the table, that voltage is plus 1.70 volts. Cadmium is going to be reduced in this electrode from cadmium to cadmium plus as a reduction potential. Its voltage is minus 0.04 volts. And the nickel that's in this one can also react right there with by being reduced, and that occurs at minus 0.25 volts. So when that switch is closed up there, what's going to happen? Which electrode, cadmium or nickel, will be the positive electrode? So you have to determine an oxidation reaction and a reduction reaction. So you've got to determine whether cadmium is going to be oxidized or reduced. Let's suppose I looked at the cadmium electrode and it's minus 0.4 volts. So I could combine that with this electrode. If I switch this around to make it electrons lost in the cadmium, I would get and combine it with this electrode, I would get plus 0.4 plus 1.70. Give me what, 1.1, 2.1 volts. And I could combine this one with this one. Now, if I would have to turn this one around with this one to give a positive voltage, because if I did it the other way, the voltages would be negative. So cadmium would have to be turned around in this one as well. So cadmium is going to be the electrode that's turned around in either case. So that should tell you the voltage that's on the cadmium electrode. Cadmium is producing electrons. That's enough of a hint. Okay. Which one is the cathode? Which one is reduction taking place? What will do the value? Read by the voltmeter. So I'm going to take the positive voltage and the negative voltage, combine them and see what the voltage would be. Which direction, left or right, does the electrons move across the switch? Now remember, the electrode that produces the electrons is negative, and electrons flow from it to the other electrode. I'm always going to look at it like that. Which direction, left or right, do the cations move in the salt bridge? Now here's what I'm going to do. Suppose, just for the sake of argument, and I'm not saying that it's this way at all, but suppose electrons came here. Negative charge comes out through here. It goes like this. Negative charge has to go the same way through the rest of the solution. So that means if electrons are coming out and going around like this, then the negative ions have to go through the salt bridge like this. So the negative ions complete the circuit that the electrons do. I always do it that way. And then if that's not the way things are going, I say, okay, well, it's the reverse of that direction. What will happen to the voltmeter reading if water is added to the cadmium cell? Now, what you have to do is see in the cadmium cell, is the cadmium ion a reactant or a product? If the cadmium ion is a product, adding water to that cell would dilute its concentration. Thus, as it shifts to the right, that increases the voltage. And then, of course, the opposite would be true for the other way around. Okay. Okay, I'm looking at this and I'm thinking that, yes, I'm pretty sure we can finish all of this next time. So in order to keep this video from getting any longer, I think I'll stop the recording now, and we'll finish up then on Thursday.